This presentation is delivered by the Stanford Center for Professional Development.
Okay, hi everyone. And so today what I'm going to be doing is moving on to starting on material in parsing. And this is the start of the section where we move on to actually dealing with whole sentences. So up until now we've done various kinds of things where we've had language models and information extraction and things like that. But essentially we've been getting or predicting little bits of information about sentences. And, well, if we really want to more do natural language understanding, it seems like we really want to know something about the structure and the analysis of entire sentences. And so that's the part of the class we start on to now. And in particular, we start on to the topic of how can we parse, meaning give a suitable structure to sentences. And that's seen as then a prerequisite for then learning more about the semantic analysis of sentences. Okay, so parsing is an area that's gone through a huge amount of very successful and good change over the last 15 or so years. So there was traditional work on parsing, which was grammar-based, rule-based parsing, and then in the last decade or so, there's then been this great amount of work in doing statistical parsing. So I just want to quickly say a little bit about the flavor of that, and then mainly we'll be going into statistical methods of parsing, and I'll say a bit about traditional parsing. Okay, so in the 1990s, there were, really for the entire history of NLP, there's been lots of work on how can you parse natural language sentences. But still in the early 1990s, essentially what you saw is that there were these parsers that had handwritten grammars, which produced detailed, actually usually richer than we often provide today, grammatical analyses of sentences. But if you actually tried to run these parsers, just pick up this morning's New York Times cover page article and start trying to parse it, what you found is that these parsers had very uneven and usually rather poor coverage. So they'd be good in a few little areas that somehow the grammar writer had worked on carefully because they really liked them, but in most other respects the coverage would be quite poor. In particular, commonly the parser would fail to return any analysis at all for quite a large percentage of sentences. On the flip side, when sentences could be parsed by the grammar, normally sentences would have many parsers. And most of these parsers actually had no good way of dealing with that. Some of them had literally no way of dealing with that and said this sentence has 1,027 parsers, and others of them would use various kinds of heuristic and ad hoc rules to favor certain kinds of analyses over others. Another problem was lots of people had lots of different parsers, but there wasn't really any way to, apart from kicking the tires and trying it on some things, there really wasn't much of a quantitative way to actually get a sense of how good different parsers were. Partly, you could sort of certainly measure on what percentage of parsers, on what percentage of sentences the parsers failed to return anything, but you kind of obviously want to know more. You want to know if they do return something, is it correct, and what's the quality of the analysis, etc., etc. Okay. But then over the last 15 years, there's then been this sort of revolution of people doing statistical parsers which are trained from data, and in practice normally the same data, which is made for an easy case of parsers being commensurable, and you can see exactly how they differ from each other. And so effectively now there's basically a commodity component of statistical parsers, and a whole bunch of people have written statistical parsers, many of which you can download and run open source. And so that's led to a new generation of sort of people being able to use parsers, because now essentially there are these good statistical parsers, which doesn't mean that they always get everything right all the time, but most of the time get most things right, which can be used, and they always return some analysis for every sentence, and so they're fairly reliable components for what they deliver. And so there's now starting to be a ton of work where people are putting parsers inside other bigger systems because it's fairly straightforward to do. And so some of the kinds of applications you see for inside question answering systems, I'll talk about those more later, but normally they do full parsing of both questions and candidate passages and documents that might contain an answer. You can actually use parsers to get a better sense of sentence structure to improve tasks like named entity recognition that I talked about before. I mean, in particular, in biological named entity recognition, I mentioned how there was often a lot of ambiguity between whether things were genes or gene products like DNA and RNA. And looking at the sentence relationships they figure in is actually a good use of information. For sentence compression or summarization, so if you want to have a shorter version of a sentence to fit on your mobile phone screen or something like that, it's good to have an idea of which bits of the sentence structure go together and are perhaps kind of little parenthetical clauses, so you can delete parts and still have a grammatical sentence that conveys the main content. Product mining, opinion mining for products. So this is kinds of things that if you want to evaluate cell phones and know why people like the iPhone, that you want to get some idea of sentence structure so you know what opinions are being predicated of the iPhone and about what attributes of the iPhone, et cetera, lots of applications. Okay, so we're going to do parsing. What's difficult about parsing? So this kind of comes back to the very first lecture when I had my whole bunch of headline sentences of funny ambiguities in parsing, which I won't go through in great detail, but I'll just do this one sentence here. I saw that gasoline can explode. So that has two readings, right? One is that there's a gasoline can, and I saw that gasoline can explode, and the other one is with the sort of fact complement, I saw that gasoline can explode as a concept. And the important thing to notice here for what we're going to do is that a sentence like this is just globally ambiguous in terms of syntactic structure. Right. That it's not like, again, it's not like what we have in programming languages, that programming languages will have local ambiguity, that sometimes you need to look at the next token to be able to decide how to parse something up. But programming languages are very carefully designed so that they only have local ambiguities. I mean, in particular, all the standard programming language syntaxes are such that you just need to look at the one next token, and that gives you sufficient information to resolve all ambiguities. Where here, you get to the end of the sentence, there's still nothing syntactically to resolve the ambiguity. The only thing that allows humans to resolve the ambiguity is using their context of how the world is. And that's something that won't be available to our syntactic processors. And there are interesting psycholinguistic angles there, which people still debate as to human beings, how much they're doing syntactic structure processing before recovering the semantics versus how quickly they're integrating the semantics as they go along. And there's some evidence both ways, but I think more and more people are thinking that there's a lot of early semantic integration as humans parse. Okay, so in classical NLP parsing, we wrote down a symbolic grammar and a lexicon. So here's my very little baby grammar. And you can essentially say that what we then did was used a proof system to prove that certain parsers followed from the words. Or if you would prefer, you could think of it as a search system and a classic AI search system. So we search for possible parsers from the words. But the problem with either of those techniques is that they scaled really, really badly. So I didn't actually put it up here, but if you remember again from the first lecture, there was that sentence where I showed some parsers of it. If Fed raises interest rates 0.5% in order to, what was it, lessen inflation or something like that. That it seems like if you kind of write the smallest grammar that you can that will produce the parsers that I showed for that sentence, it actually produces 36 parsers for that sentence, which already seems a kind of a frightening number. I tried it out on a small context-free grammar that I'd written for other purposes, which only had 10 rules in it, and that 10-rule context-free grammar gave 592 parsers to the sentence. And well, if you then start running it on a bigger context-free grammar of the kind of robust context-free grammars that you use for general text, what you actually rapidly find is that you'll have millions of parsers. most of which are incredibly weird and unlikely looking, but are nevertheless licensed by the grammar. In fact, as we'll discuss later, for certain ways of building tree banks, from building grammars from tree banks, that technically the kind of grammar you're using actually licenses an infinite number of parsers for sentences because it can just kind of build infinite structure up above sentences. Okay, so the problem with non-probabilistic parsing was that there essentially wasn't a good way to solve that problem. So if you looked at your 592 parsers, the obvious thing to think was, well, maybe I can put more constraints on when rules can apply so I can get rid of some of those weird and unlikely parsers. But the problem was that, on the other hand, the more that you put in those kind of constraints, the more there are sentences that you failed to parse at all. And so you had this coverage problem. And so that there were these two things that were kind of beating off against each other, and categorical methods just didn't give a good way to find a nice middle ground. And so effectively that's led to the movement to probabilistic models for parsing, where the whole idea then is to say, well, really we're just going to be interested in what are the likely parsers for this sentence. And so typically that means that the style of the way statistical parsers work is that they still have a grammar, but their grammar is actually extremely, extremely loose, so that there's no real attempt to constrain what's possible inside the grammar, which is what leads to the thing I just mentioned about often the grammar actually licenses an infinite number of parsers for a sentence. And all of the action is then in the weights or probabilities of the grammar, which are then trying to decide what are the likely or unlikely parsers for the sentence. And going along with that, there's then some clever algorithms and programming to make sure that despite the fact that you theoretically have an infinite number of parsers, in practice you can actually find the good parsers very quickly. Okay, and so what's enabled statistical parsing? I mean, so part of it you can obviously go back to the whole history of AI and the logicist tradition, and people weren't very empirical, and ways of thinking that dominated AI and were reflected on what people did with NLP. But as well as that, I mean, the huge requirement of being able to do probabilistic parsing is actually to have the data to make it possible. So if you look at the history of statistical methods in parsing, that in around the sort of late 80s and early 90s, there was already an intense interest in using probabilistic and machine learning methods for NLP, and people started to do some work looking at unsupervised methods of learning parsers. But the problem is that those methods just didn't work very well. Now, much more recently, I myself, with students, have done some work on unsupervised parsing methods that work a lot better, and I can mention that a few weeks hence. But at least at that time, the attempts to do unsupervised parsing were just really, really poor. And so what really transformed the ability to do statistical parsing research was actually having supervised data. And to this day, if what you want is a high-performance statistical parser, it's trained on supervised data. And so it's really the building of tree banks that enabled this whole line of enterprise to flourish. And so what is a tree bank? This is one sentence from a tree bank. So what a tree bank is to a first approximation, you get people who are willing to work long hours for low pay, and you give them sentences, and they have to put syntactic structures over sentences. So this was the most famous. There are now kind of a lot of tree banks at different places, but the most famous tree bank, and still by far the most widely used one, is the Penn Treebank, which was done at the University of Pennsylvania starting in the late 80s, and it kind of became generally available to people in 1993, so that they spent several years with several students and other research staff putting tree analyses over about 50,000 sentences. Most of the work was actually done by classic students. It turns out that classic students, I guess some combination of they have a good understanding of traditional grammar. They know what nouns and adverbs are. They don't have a lot of other employment opportunities, and It turns out that linguists argue too much, right? They're always dissatisfied with an analyses of different things and want it done differently and better, whereas, you know, classic students are more willing to go with, okay, these are the rules and this is how you're meant to do things. So this is what a Penn Treebank tree just natively looks like if you open up a file, which you have to do for the third assignment. And so, you know, reflecting the times of those years, it sort of has this Lisp S expression kind of style, but you can fairly easily see how to interpret it as a tree. So we have words, they have part of speech tags, they go into phrasal constituents, and then that all adds up into a bigger tree. And so essentially what a Penn Treebank tree gives you is this context-free grammar or phrase structure grammar analysis, but actually gives you a little bit of extra stuff, and so it's worth just sort of being aware of some of the extra stuff. So there are basic categories like sentence S and noun phrase, NP and PP here. I mean, sometimes those categories are given a little bit of extra information about their function. So this is saying this is an adverbial sentence, so it's sort of adverbial modifying sentence to the main clause. This noun phrase here is the subject of this sentence. This PP here is a locative prepositional phrase. So those are referred to as functional tags. Most of the time when people are doing basic context-free grammar parsing, they just strip them all off as they read in the sentences. And that's what our pre-processing will do for the parsers you guys build. But then the second bit is there's then under the NP subject, there's this none star. Because actually, if you read this sentence, the move followed ... reflecting a continuing decline in that market. But the point here is there isn't actually any subject direct subject for the verb reflecting, that is this participial sentence. And really what the subject is this whole big sentence up here. So the Penn Treebank also postulates various empty nodes, which are kind of seen as syntactic structural elements, but that aren't directly pronounced words. So another thing, if you actually want to parse sentences as that they're said, is that normally people strip out these empty nodes as they read things in. Not in my picture here, but commonly the empty nodes then also have numbers on them which are used for cross-indexing. So you can see what is taken to be the subject of the verb reflecting. So you'd have star -1 here, and then the -1 would be co-indexed with the whole main sentence up there to say all of that should be taken as the subject of reflecting. And so effectively that means it gives a little bit of extra structure that's beyond the context-free grammar, which some work has explored quite a bit for resolving things like deeper dependencies in sentences that aren't directly reflected. Okay. Yeah, so in retrospect, building tree banks has just been a marvelous thing for the field of natural language processing, and you know, it's kind of not clear why it didn't get done 2-3 decades ago. Because even if you weren't thinking very probabilistically, in retrospect it seems like, well, surely having tree banks would just be a marvelous idea, because then everybody could evaluate their parsers and see how good their coverage was and compare it. We have a good sample of English, so we can see what phenomena parsers do and don't cover and where their grammar should be extended. It seems just a generally useful concept, but I guess a lot of things seem a good idea in retrospect, but somehow weren't obvious to people at the start. And I mean, I think one way of thinking about it is, if you're starting off with nothing and you know, say you're writing one of those Zork-style games and you want to be parsing up commands like throw X at dwarf or something like that, well, you know, the most obvious thing to do is start thinking of, okay, well, I'll have a lexicon of some verbs like, you know, throw and open and go, and well, then I can have an object of throw axe, and then I can have prepositional phrases and start building a grammar to go with your lexicon and doing it by hand. That's just kind of the obvious thing to do. The obvious thing to do is not to write down a lot of possible sentences and start parsing them all by hand. I mean, doing the latter actually seems like it's way more inefficient than coming up with a grammar, because the whole idea of a grammar is that it generalizes over a lot of examples. So a grammar is a much more compact representation of possibilities than actually writing out all of the examples. So, you know, treebank building seems like a very inefficient, painful, and expensive process to undertake. But in retrospect, it's really turned out to be the opposite, because if you look at the history of NLP, that sort of from 1965 to 1990 approximately, that if you add it all up in person years, you can kind of identify dozens of projects where people built grammars and parsers to go with those grammars, and in total spent tens of person years on those activities of coming up with good parsers. But the legacy of that work is essentially zero. Well, there's some conceptual legacy, but in terms of having something useful from what we do today, the legacy is basically zero, because every one of these grammars was written in some different formalism by some different person and had a lot of knottiness in it, and essentially, you know, no one would deal with any of them today. Whereas the Penn Treebank has just been such a wonderful reusable resource, and so that now, 15 years later, everyone is still using it for everything, and so it's had this huge multiplier effect in terms of reusability. And it has all the other good goals of providing an evaluation standard, gives broad coverage of real linguistic constructions. Since you have parse trees, you can simply count things, so it's good for frequencies and probabilities. And it now gets used in all sorts of other places as well. So more and more so, you know, linguists were slow to discover the Penn Treebank, but more and more these days that people doing linguistics, when you want to investigate a phenomenon, you know, it doesn't answer all questions, but one of the easiest and best ways to get a reasonable idea of what are the possible variants of this construction that occur in actual usage is actually to go and look in the Penn Treebank and find examples of that structure. And so there are various tools that are then available, including we've got one that you can download from our website, which are effectively then pattern languages where you can search over Penn Treebank trees. Okay. Well, what is linguistic structure? I'll come back to the alternative later, but I just want to mention the two main kinds of linguistic structure people use. The kind I've already drawn and shown you, and what the Penn Treebank natively has, is constituency structure, otherwise known as phrase structure, otherwise known as a context-free grammar. And so if you draw it prettily as a tree, you get something like this: Fed raises interest rates. Okay, so what this kind of structure is all about is making claims that certain things are constituents. So it's claiming interest rates is a constituent. And constituent just means something that goes together and acts as a unit. And so if you really want to know a lot about this, you have to do a linguistics class. And they're lots of fun. You can go into a syntax class and learn all about how people work out constituency and why different theories do different things. But in very brief, you know, there are lots of, these are the kind of evidence people use for constituency. So that if you have groups of words that kind of sort of move around as a unit, that's evidence that they're a constituent. So you can say, John talked to the children about drugs, or John talked about drugs to the children. So the fact that you can swap those two units makes it look like both of them are constituents. Whereas you can't take, okay, let's take these four words, drugs to the children. Can I swap them around and move them around? So if you try and swap that with the remaining words John talked about, you then get John talked drugs to the children about. Doesn't work, right? So that's evidence for that being a constituent. For something like interest rates, it's kind of harder in a four-word sentences, but you can do things like topicalize it. So interest rates, lately the Fed raises and drops them a lot, or something like that, that it can appear different places. Other ideas of constituency is if things are a constituent, that normally you can expand it and contract it in various ways with things that are of the same semantic type. So from I sat on the box, you can expand it into a bigger prepositional phrase. I sat right on top of the box. Or you can shrink it down to a single word that can act in the place of a prepositional phrase. So I sat there. So these kinds of words are called proforms. The most common and ubiquitous form of proform is pronouns, which you can use instead of noun phrases. So that's he, she, it kinds of words. But you also get proforms like there for other categories like prepositional phrases. And there are lots of other tests. Coordination, blah, 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 blah. Okay, so there are two claims here. I forgot the second one. The first one is that this acts as a unit. But the second claim is then that we can have types of these units. So the claim is this is a noun phrase, and that means that there's a class of constituents that behave the same, meaning that they can appear in the same kinds of positions. So the claim is that interest rates is a noun phrase, and Fed is a noun phrase, so that they should be substitutable without mauling the syntactic structure. So you should be able to say interest rates raises Fed. And it's kind of hard to make semantic sense of that. But, it's syntactically well-formed, with Fed being a proper noun. It's a good syntactic structure. Okay, then here's the other alternative, which is dependency structure. So the idea of dependency structure is that it shows you which words are direct arguments or modifiers of other words. Okay, and there are at least a couple of ways of representing dependency structure. This is actually the original and traditional way of doing it when it was proposed with arrows. And here's a way of doing dependency structure as a tree. And so what you're doing is, so here we're following out arrows to their points. So the tail of an arrow is where the head is, and the pointy bits point to the dependents. So here put has 3 dependents: boy, tortoise, on. And so they're the 3 arguments of the putting event. Boy has a dependent of the, because it's the boy, as does tortoise. And then on has a dependent of rug, which has a dependent of the, which you can also represent like this. So put has its 3 dependents, and then they have their dependents under them. And I just sort of slanted these arrows to represent word order, but you kind of don't really have to do that. Okay, so a dependency structure is directly showing these word modification relationships, but only indirectly showing constituency. It actually does show constituency, because if you kind of take subtrees here, or if you kind of take the closure of something and all its dependent arrows, that does show you constituency. But constituency is sort of latent in that picture. Yeah. So that is a good question and a good thing to think about. And the answer goes like this. If you look at this graph, its great property is that there are no dependencies that cross. If you have no dependencies that cross, that means your dependencies are such. That means for the implied constituency of that dependency graph is always a tree. And so, yes, you can convert it into a tree. So your question comes down to, do you get dependencies that cross? And the answer to that is, yes, you do, but not very much. And you might think that that's an unsatisfying answer or not. So, I mean, the kind of place that you get dependencies that cross is with special constructions like questions. So if you have a sentence like, what did you buy at the store yesterday? And you say, okay, what? That's serving as the object of what was bought, and therefore bought will be taking a subject of you and an object of what, but then it will also take a argument of where at the store and an argument of when yesterday, then the what arc is going to cross over the when and where arcs, and you have crossing dependencies, which means that you can't represent it as a tree. But, you know, essentially, in natural languages, crossing dependencies are rare. They occur in these special kinds of circumstances. So they appear in English when you've got question words like that that are fronted to the front of the sentence, which is sort of in some sense a weird feature of English, right? That in terms of sort of the normal placement of the words, what you should say is, you bought what at the store yesterday, right? That'd be kind of maintaining the normal placement of words. And you can say that kind of question with some question intonation, and people sometimes do, but it's not the usual way to say it. The questions in English have this funny marked syntactic word ordering. And the other place you can get is you can get things moved to the end, which is then called extraposition. Especially when they're kind of big new constituents, you can say something like, I bought at the store yesterday the most amazing red tricycle you've ever seen, or something like that. So, yeah, you get things that are not trees. What do people do about that? It varies, but what the Penn Treebank does about that is it represents it as a tree anyway. And so in the Penn Treebank and context-free grammar parsing, everything is always represented as a tree, and things that don't fit into that tree structure are handled by other mechanisms. So if you have something like, what did you buy at the store yesterday, that what would be just attached to the sentence as, okay, here's a WH word at the start of the sentence, and would be given tree structure, and then the connecting between what and the object of buy would be done with these kind of empty nodes and co-indexing that I was mentioning earlier. Okay. Yeah, so this way of thinking about things with dependencies is sort of not the kind of the context-free grammar way of thinking about things. But if you're thinking about it in terms of meaning relations from sentences closer to what we're doing with information extraction, this is sort of actually a very natural way to think about things. And I think, you know, if you look at the history of parsing in the United States, traditionally there was extremely little usage of dependency grammars. Dependency grammars were invented in Europe, and constituency parsing was really what everyone did in the United States. But in the last 10 years, I think there's sort of been more and more recognition that this dependency grammar format is actually a very convenient representation for various kinds of surface semantics and more use of it. Nevertheless, notwithstanding that, I will talk first about constituency parsing and then get back to dependency parsing later. Okay. But, you know, either way, you know, formally there's an isomorphism between dependency grammars with no crossing dependencies and headed context-free grammars. The crucial extra information you have in a dependency grammar is you're choosing one child of each node to be the head child of the node, and the other nodes are then its dependents. So there are close relationships, and the kind of questions of interest are the same. So if you think about parsing, effectively the key decision that we make in parsing is deciding which words modify which other words, which you can represent in either a phrase structure manner or a dependency structure manner. And so that leads back to these ambiguities that we saw at the beginning, that if we have, I saw the man with the telescope, it has two possible parsers, which here I'm representing in constituency fashion. One in which we're building this big noun phrase, the man with the telescope, where with a telescope is modifying man, and the other one in which with the telescope is under the verb phrase and is modifying the verb. Okay, and so it's that choice of what does with a telescope modify, which is essentially the key parsing decision that we have to make. And those decisions are often referred to as attachment decisions. So I guess this is sort of thinking of pin the tail on the donkey or something like that, that you're working out where to attach this phrase into the sentence structure. Okay. So how do we do it? Well, one answer to that is, of course, this is an AI complete problem. Use every bit of knowledge you have about world knowledge, context, sentence prosody, ... and you put it all together and you make the right decision. And in some sense, that's the right answer and appears to be what human beings do. But it turns out that you can actually get quite a long way using fairly simple statistics to work out these kind of attachment decisions. And, you know, the first way in which that was explored, which to a first approximation turned out to be the wrong way, was to say maybe we can use straightforward syntactic factors to decide what are likely attachments, or even what is the attachment that a human being will choose. So this work was actually explored in the psycholinguistics community. And so early on, people proposed structural factors of sentence structure which would determine how humans would resolve these syntactic ambiguities of PP attachment. So in particular, Kimball in 73 proposed the principle of right association, which said that you should attach a PP low or near. So that gave you early closure. So Kimball would say, okay, we've got with a telescope, how you should attach it is to the low nearby thing, the man, and prefer this structure. Not that different in time. There was actually then Lynn Frazier, another psycholinguist. She proposed the principle of minimal attachment. And minimal attachment, what it predicts actually depends on the details of your grammar structure. But for the particular kinds of grammars that she was considering, low attachment, it turns out, actually predicts in this case exactly the opposite. So it would be predicting that the PP should be modifying the verb phrase. So obviously, both of them can't be right in what their predictions are. And so the obvious question is to say, well, which of them is right? And the answer is sort of sometimes one, sometimes the other. There is a structural preference. So if you're just going to have this as the only factor in your model, that the actual statistics run in favor of Kimball. It's more common to do attachment low to the nearest thing. But that's not a very strong predictor. It depends on what corpus that you count over and what the nature of the writing is about, etc., etc. But it turns out that most of the time in English, it's somewhere between 55 and 66% of PPs attach low to the nearest thing next to them. So, you know, that's a little bit of a preference. That helps a little, but it's clearly not a very strong preference. But, you know, there was a certain blindness, I guess, in the kind of work that was done in these days, where basically everyone was very infatuated with Chomskyan grammars and looking at grammar structures and predicting, trying to come up with structural factors that would predict things, that no one was paying very much attention to words. And so it really wasn't until kind of about 1980 that people made the, in retrospect, kind of obvious observation that, look, you can get a lot of information about how best to attach things by just looking at the words. So even with a kind of a made-up example like this, the children ate the cake with a spoon versus the children ate the cake with frosting. You can kind of think, eat spoon, that's probably kind of common. Eat cake spoon, probably not so common, you know. I guess it occurs, but, you know, overall, eat spoon's probably more common. Cake frosting, that's very natural. Eat frosting, possible, probably happens less. That sort of seems like the words should be used more useful. And well, really, this is the kind of example that's made to be ambiguous. If you actually kind of take real text sentences, that most of them seem that the words much more strongly determine things. So here we have Moscow sent more than 100,000 soldiers into Afghanistan. Send into, that's a very common idiom. Soldiers into Afghanistan. Soldiers into, doesn't seem to work. Sydney Water breached an agreement with New South Wales Health. Agreement with, that's a very common pattern that you see a lot. Breached with doesn't sound so good. So it sort of seems like we could use information about the words to resolve prepositional phrase attachment ambiguities. And so that was what was proposed in a new thread of work on lexicalist grammars by Ford, Bresnan, and Catalan. Joan Bresnan's here in the linguistics department. So they say what in retrospect is maybe sort of seems kind of obvious. It is quite evident then that the closure effects in these sentences are induced in some way by the choice of the lexical items. Psycholinguistic studies show that this is true independent of discourse context. Okay, so that suggests a really simple way to work these things out. So maybe we could just do a likelihood ratio. So we can have a likelihood ratio of the probability of seeing a certain preposition given the verb. So that's kind of breached with, sounds unlikely, versus the probability of the preposition given the noun. Agreement with, that sounds pretty good. And if you do some data counts, you find that out. That you get a lot more of agreement with, and so your likelihood ratio favors about 7 to 1 going with a noun attachment. So that works out fine. Does this always work? Well, just doing that doesn't always work. So here's an example where it goes wrong. Chrysler confirmed that it would end its troubled venture with Maserati. So I got some statistics where I've calculated from a fairly big corpus so the counts of the words, counts of the word co-occurring with. I do my divisions to get kind of maximum likelihood estimate probabilities. And if I do that, it's kind of close, but winning by a hair is end with occurs more often than venture with. So I would give, and that's because the phrase end with does occur a lot in contexts like theatre or musical shows. The performance ends with whatever it is. And so if I just used my likelihood ratio statistic, I'd get it wrong. I'd predict that in this example that with Maserati would be modifying ends rather than venture. And that's clearly wrong. Now, I mean, of course you could just react to that and say, well, you know, that's life and statistics. You make a prediction. Sometimes you get it right. Sometimes you get it wrong. You found the example where you got it wrong. What's the problem? And, well, you know, to some extent that's true. But it seems like the problem is more, there is a deeper problem here that suggests that we want to do something different. Because, yes, it's true that ends with occurs quite a lot with my examples, like the show ends with an amazing spectacle. But if you kind of think about those sentences, basically they're actually intransitive sentences, where it's not Chrysler ends the venture with a prepositional phrase. Those are sentences where end isn't taking any direct object at all. It's just this ends with a standing ovation, that you're getting kind of an intransitive use of ends with then some PP after it. So it seems like somehow we should be using that bit of information. It turns out that there's actually another bit of information that we should be using as well. So that if we construe with Maserati as modifying end, and if we take it that we're going to have a grammar that is a context-free grammar that's tree-structured, so we don't have any of these crossing dependencies, well then, if we take that analysis, we're also making an implicit decision that venture doesn't have any material following it, because it then couldn't have any material following it that wouldn't involve a crossing dependency. So it seems like for this example, what we're really doing if we do an attachment of with to end is we're implicitly also making a decision that venture doesn't have any modifiers coming after it. And we weren't modeling that decision at all, which is sort of what it says on that slide. And so essentially, when we do parsing, what we're doing is saying, well, you know, it's just not enough to take one particular fact like what should this prepositional phrase modify, and, you know, count up some stats and do some likelihood ratios and make the best guess. Because actually, coming up with a parse for a sentence is a big joint decision, and any decisions that we make about one thing are influenced by and in turn determine a lot of other things. So that if we're saying that with modifies ends, well then we're implicitly making a decision that nothing modifies venture, and that's maybe unlikely, and there are all of these decisions mesh together to come up with the right analysis of the sentence. So essentially what we'll want to do is come up with some kind of joint model where you can make all of these parsing decisions at the same time and come up with the best global analysis for a sentence. Okay. And so, I mean, and part of what we'll want to do is sort of use more information. So typically if we want to do a better prepositional phrase attachment model, that we'll want to know what the verb is, what this noun head is, what this preposition is, and also what that noun head is. So that's kind of the minimal amount of information you can have to make a sort of a semi-decent prepositional phrase attachment analysis. And it turns out that if you provide that much information, you can actually do reasonably well just with lexical factors, that you can get accuracies well up into the high 80% in doing prepositional phrase attachment. Okay. Here's just one example from a real sentence, just to show that prepositional phrase attachments in practice actually get very complex. So if you look, you know, not every sentence, but if you just look through a bunch of Newswire sentences, you can go and read the paper when you go home and feel good about it, that, you know, there are just tons of sentences that, you know, essentially just have series of prepositional phrases. So here's one that I picked out from a boring article where what we find is there's just this sequence of 4 prepositional phrases after the basic verb. And the thing to notice is that they actually kind of have this sort of weird pattern of dependencies. Okay, so the board approved its acquisition. So by Royal Trust Co. Limited, you know, theoretically couldn't modify either the verb or the noun. It modifies the nearby noun, so it goes with Kimball. Right? Of Toronto then modifies the noun phrase inside the prepositional phrase. That also goes with Kimball, modifies the nearest thing. But then for $27 a share, doesn't modify this noun phrase, doesn't modify this noun phrase, but modifies this noun phrase. So that's a long distance attachment. And then at its monthly meeting is doesn't modify this, doesn't modify this, doesn't modify that, doesn't modify that, goes all the way right up to the top, and it's then modifying the verb at the top. Okay, so we've sort of showed lots of examples that if you had verb, noun, prepositional phrase, you got 2 parsers, which correspond to the verb and the noun attachment. If you have verb, noun, prepositional phrase, how many parsers do you get? So that's up to here. So this one could modify here or here, and then this one can modify here or here or here. And then there's this slight trickiness because we're insisting it's a context-free grammar, so that the modifications have to be nested. Well, if we had no constraints, how many possible modification structures could we have? No. Oh, what was it? Oh, no, you're right, we do. Sorry. Yes. Yes. Okay, right. So if there, yeah, you're right. Sorry. If there are no constraints, this one has 2, this one has 3, this one has 4, this one has 5. So yeah, it's n factorial. Sorry. Okay, but we do get a constraint because effectively here, because of the nesting relationships, that we effectively lose one. So that for 2 PPs, the number that we actually get is 5. And if you want, you can try drawing it out on a sheet of paper and check that you get 5 of them. And then if you go to then have 3 PPs, the number that you get is then 14. And it goes up like that. And so actually the number that you get is the Catalan numbers, which effectively is a series which you can look up on Wikipedia if you're into these sorts of things. It's a series of numbers that turns up in a lot of places where you have tree structuring. So another, for those people who remember with joy doing 228, another place that the Catalan series turns up is if you consider the number of triangulations you can get for polygons of different sizes, that's also Catalan numbers, because effectively you're making successive choices as to how to divide the polygon that remains to get smaller things until you get triangles. Yeah, so at any rate, the important thing to know is the number of parsers you get here goes up exponentially with the number of PPs that you attach. Okay. Okay, so somehow we want to deal with having all of those attachments and still parse efficiently. So parsing basically means, take grammar, take sentence. Now the grammar is written down to sort of generate sentences. It says S goes to noun phrase, verb phrase. Noun phrase goes to determine a noun. So what we want to do is run the grammar backwards and say, okay, here's a sentence. What underlying or hidden structures could be behind this sentence? And so you can think of that as a search problem. You can think of it as a hidden data inference problem. And for starting off for looking at parsers, we're essentially going to look at algorithms that can actually generate all of this possible structures according to a grammar that can underlie a sentence. And then we're going to very quickly shift and say, well, what we're going to want to do really is find out something that gives us the best parsers according to a model. Okay, but if you think of this as a search problem, you can think, okay, well, I know something about search. There were things like depth first search and breadth first search, and that's true. You can apply either of these here as a search problem. There's also another distinction in terms of parsing, which is there are 2 directions to do parsing. You can either say, okay, I want to parse a sentence, and sentence can go to noun phrase, verb phrase, or perhaps sentence can go to a question form where you have auxiliary, noun phrase, verb phrase, and then sort of work downwards. Or else you can say, okay, the sentence I want to parse is Sydney Water breached its agreement. Let me start with those words. Sydney is a proper noun. Let me turn into a proper noun and work upwards. And so those are referred to as the top-down parsing and bottom-up parsing, for which direction you go. And that choice of top-down or bottom-up parsing is just independent from the search strategy of whether you do breadth first or depth first parsing, and you can do any combination of those things that you want. So if you're not going to be confused, you want to sort of separate out 2 notions. One notion is what you're doing with the tree, and so for the tree you can work bottom up or top down, and so at any point your state in the search is a piece of the tree effectively. And then separately you have this second tree, which is your search tree, and it's inside the search tree that you're then doing something like breadth first, depth first, iterative deepening, or one of these search strategies. Okay, so here's our simple little phrase structure grammar. Normally, by convention, people call S the start category of their phrase structure grammar, and when it's not written down, you assume that. I mean, actually, if you look at the Penn Treebank, it has an extra node above S, which is normally referred to as root or top, which is actually really useful in practice, because it turns out that not all sentences in Newswire are sentences. Sometimes they're just a noun phrase or a fragment like a prepositional phrase. So you'll have a headline that's something like off with his head or something, and that's just a prepositional phrase. So it's useful to have a kind of an extra category up the top, like top, which you can then have a probability distribution over how often you get a sentence versus a PP fragment. Okay, then this is stuff you should have seen in some class where we have context-free grammars with a set of terminals, a set of non-terminals, a start symbol, and a set of production rules that rewrite them. I will mention only one qualification on that, is in practice for the way natural language grammars are written because of the way natural languages are, is that people always make a very clear distinction that isn't in the traditional CFG formalism between pre-terminals, which are categories that rewrite as actual words, versus the higher level structural units. So the pre-terminals are our parts of speech, like noun and verb, and adjective and pronoun. So pre-terminals are non-terminals, so they're a subset of n, but they always rewrite as a single word. And then you have other categories like noun phrase, verb phrase, sentence, which will rewrite as some combination of other non-terminals and pre-terminals. And people do that just because it's a manifest fact of natural languages. So the thing is that you have a humongous number of words, you know, a complete dictionary lists 200,000 or something, which you fit into a small number of parts of speech. Traditionally, people were taught 8, but even if we use something like the Penn Treebank tag set, you know, excluding punctuation, there are only 36 parts of speech. And so then the real grammar is being written in terms of the phrasal categories, rewriting as those pre-terminals, which then rewrite as a huge number of terminals. Okay. And these are the traditional properties of grammars. So you have parsers. A parser is sound if it doesn't screw up. Everything it returns is something that should be built by the grammar. It terminates if it doesn't go into an infinite loop. And it's complete if you can give it a grammar in a sentence and it produces every valid parse for the sentence and terminates. And so, you know, traditionally this was kind of write a parser that you wanted this property. But, you know, in practice when we build statistical parsers, a lot of times we forget the completeness property. So we want a sound, obviously we want a sound parser, and we want a parser that terminates, but we'll be completely happy that the parser isn't complete, providing the incomplete set of parsers that's returned to us includes all the really good and likely ones. Okay, so I'm just going to kind of really quickly say how you do top-down and bottom-up parsing as search processes, and then I'm going to get into how people really do parsing as a dynamic programming process. I could ask, has everyone seen, you know, doing top-down and bottom-up parsing in some class? Yeah? Are there people who haven't? If you haven't, you can read all about it in Jurafsky and Martin, and I won't do it here. Okay, but I mean, essentially what I just want to clue people into is if you kind of read your compiler's book, you get taught about top-down parsing, and you get taught about bottom-up parsing, and in practice people, you know, normally use bottom-up LALR style parsers. That's not really effective for what we want to do. And so I just want to kind of clue people into what the issues are there. And the reason it's not effective is this issue of global ambiguities. Okay, so top-down parsing, here's my little picture that's too small to read, but you just kind of have to see the shape of it. So what I have here is the outer tree is my search tree, and then the inner trees, which are too small to read, are then a representation of my state in the search. So I start with just my top, my start rule. I then expand it in every way that's licensed by the grammar, which is only one for the first rule. But then I have I expand the left noun phrase, and I can expand it in 3 ways. And then I keep expanding down, and I would eventually start producing words. So here I produce cats, and here I produce people, and I do this top-down search through the grammar. Okay, so this is a possible thing to do. Actually running top-down until you actually produce words is obviously horrendously inefficient. No one ever did that. People would top-down parse until you got to pre-terminals, and then you do dictionary lookup to see, okay, is the first word in the sentence clause, can it be parsed as a noun or something like that? Okay, so top-down parsing has various problems. A first problem is left recursive rules. So if you have left recursive rules in your grammar, which natural language grammars just do, so basically everyone wants to have a rule in their grammar that is noun phrase rewrites as noun phrase conjunction noun phrase, because you want to have the boy as a noun phrase and you want to have the boy and his dog as a noun phrase. And so that's a left recursive rule because the head category noun phrase is also the leftmost category. So if you have left recursive rules, top-down parsing doesn't terminate. Well, there are things you can do about that, and things in various ways. You know, there are various problems. These ones are all solvable in various ways, which I won't go through. The problem that kind of just isn't solvable is doing a top-down search leads to repeated work anywhere there is common substructure, and I'll show that in a minute. In reverse, you can do bottom-up parsing. There are different ways you can do bottom-up parsing, but the most traditional way to do it is this thing called shift-reduce parsing, which you should have seen somewhere. And so in shift-reduce parsing, you're doing these two operations of shift where you take the next word and start considering it, and reduce means you apply a grammar rule backwards. So here I'm showing one search path vertically down as a choice of shifts and reducers, but because you often have a choice as to whether shift or reduce, that gives you all the different search paths that I'm not showing you. So the sentence is cats scratch people with claws. So at first I can just shift it on, have cats, then I can reduce it as a noun, I can reduce it again as a noun phrase, I can then shift on the word scratch, I can reduce it as a verb, I can then shift on the next word, people, I can reduce that as a noun, I can reduce noun phrase goes to VNP here by reducing noun to noun phrase. And at this point I could have kept reducing, I could have said VNP, that's a verb phrase, NPVP, that's a sentence. Okay, I've reduced to the start category, but the problem with that analysis is that I've left some of the words on the input still there. So the right thing to do is to keep shifting, and I can kind of start shifting again, and you can parse the sentence. And different choices of shifts and reducers then give you the different analyses. And in programming languages, you're allowed to have shift-reduce choices, which are always resolved in favor of shifting, and that's what gives you that the else goes with the closest if rule. But you're not allowed to have reduce-reduce conflicts, that if you have those, your grammar compiler tells you that you messed up badly and go and fix it. And a reduce-reduce conflict then corresponds to what we're calling an attachment ambiguity. So whether you have the prepositional phrase go with the noun or the verb, that's then a reduce-reduce conflict. And what we want to do here is say, well, both of those are good analyses, and we want to find all of them, which you could do by exploring the full search tree. Okay. And bottom-up parsing, you know, it can also has various properties of good and bad things, but essentially what I want to just get to is this repeated work property. So here is my wonderful picture that I slaved on mightily on PowerPoint, which is meant to show you in very small print the problem of repeated work. I mean, it's a little hard to get a sense of the problem of repeated work and why it's the killer problem when you're just looking at 5-word sentences. So I've labeled it a bit further, and I have this 7-word sentence, cats scratch people with cats with claws, which is licensed by my same teeny grammar, and which starts to be big enough to show the problem of repeated work. But essentially, that as your sentences get longer, the average length of a sentence in something like the New York Times or the Wall Street Journal is around 23 words. There's sort of this skewed distribution. You start getting quite a lot of probability mass around 15 words, and then it stays pretty high through about 50, and then it kind of really tails off, though there are some sentences that go out into 100, 200 words. So as you start getting into longer real sentences, like those 20 or 30 word sentences, what completely kills you is this problem of repeated work. And that problem of repeated work is essentially coming from this problem of attachment ambiguities, like with the prepositional phrases, where you start getting this exponential number of parsers. So here I've got the 2 PPs with cats, with claws, and I've got here the 5 allowed parsers of that sentence. And I'm not actually showing the search trees in either a top-down or a bottom-up manner. I'm just showing you the possible structures for this sentence. But the thing to notice is that these 5 sentence structures have large pieces of common substructure. So here's the verb phrase, scratch people, in this parse. That verb phrase also occurs in this parse. Here's this big PP with cats with claws. That big PP also appears in this parse, exactly the same. This big PP contains in it this smaller PP with claws. And while that smaller PP with claws, it actually appears in every parse. It appears here, 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 and over in this one, even though I haven't shown it. And here is this noun phrase, people with cats. That noun phrase occurs here, and it occurs here. So all of the parsers share huge amounts of common substructure. And so the problem is that if you do any kind of conventional search, either top-down or bottom-up, down each search path, you'll be doing all of the work of discovering those same bits of common substructure over and over and over again in every search path. And so that means that you do this enormous amount of repeated work. And in fact, you do an exponential amount of repeated work. So that the key result is using any of these simple parsing techniques for natural language grammars lead to parsers that are exponential in their runtime. And so that's kind of bad news. And so what we want to do when we parse is not do exponential amounts of work. Okay. So this is sort of summarized here. Okay, so you can solve the various problems with left recursion, etc., in various ways, but the big problem is these global ambiguities. Okay, so that means that you want to do something different about these structures. And the standard solution, and the one that I'm going to start into, is to say, okay, well, what we should do is come up with a dynamic programming algorithm to do parsing. And that just is the standard solution, and I'm going to present in particular the method of parsing, which is called CKY parsing, which is an old traditional method of parsing, invented in the 1960s. This part isn't the latest science. Of course, it's not the only way to solve this problem, and I'll mention quickly a couple of alternatives. So, from AI class, you could say, well, you're doing tree-structured search. If you're doing a graph-structured search, then you could recognize these common substructures and do things only once. And that's possible. A simpler way of doing it, which works kind of nicely, is to use the idea of memorization. So if you make sure you remember work that you've already done, you can avoid the problem that way. Okay. Just one slide to talk about human parsing before we get back to machine parsing. I mean, human parsing is kind of interesting, and some people find it so interesting that they do psycholinguistics as their profession, that if you think of different structures for sentences, well, humans have this problem of an exponential number of parsers. What do they do? And it sort of seems like there's an interesting combination. On the one hand, there are lots of cases in which you have starts of sentences which have many different continuations with different grammatical structures, and it seems like human beings just never notice and there's no difficulty at all. So if you start off saying the words "have the police," well, those three words can have several different syntactic structures as these continuations show. So if the sentence is, "have the police eaten their supper," well, that's a question where the "have" is an auxiliary and the police is the subject. Whereas if you have the sentence, "have the police come in and look around," there the "have" is an imperative verb and the police is the object of having. And if you have the police taken out and shot, that one's also an imperative style. So you get these different syntactic structures, but it doesn't seem to worry human beings when they start to listen to words. On the other hand, it doesn't seem like human beings maintain ambiguities forever. In other situations, it seems like they do commit to analyses. And so that's referred to in a lot of the psycholinguistic literature as the phenomenon of garden pathing, where the human will take one analysis and commit to it. And you can detect that because if you then give an unexpected continuation, the human being kind of goes, "Ugh," and you know, they can reset themselves and start re-understanding the sentence, but it's clear that their processing has been disturbed, and that's referred to as garden pathing because you've been led down the garden path. And so that's sentences like these. The man who hunts ducks out on weekends. Doesn't work. What's the analysis that works? The man who hunts ducks out on weekends. Or the cotton shirts are made from grows in Mississippi. Doesn't work. It's meant to be the cotton shirts are made from grows in Mississippi. Okay. So I've only got a few minutes left now, so I'm not going to have time to show CKY dynamic programming algorithm for parsing this time, so I'll do that at the start of next time. But I'll just start to say, introduce probabilistic context-free grammars before we finish up. Okay, so most of what we're going to be doing is parsing with probabilistic context-free grammars. And so essentially they're exactly the same as the context-free grammars that I mentioned before, apart from we add one thing to it, and that is we've got a whole bunch of rules like a context-free grammar, and for each of those rules we then give a probability to that rule. These are probabilities of rules given their left-hand side. So the property that we have for these probabilities is you have some category like, say, verb phrase, and the probabilities of all of the ways of rewriting verb phrase add up to 1. So we might have verb phrase goes to verb, intransitive verb phrase goes to verb, noun, phrase, transitive verb phrase goes to verb, noun, prepositional phrase. We saw those, and you take all of those rules for rewriting verb phrase, and the sum of their probabilities will add up to 1. And if we say no more than that, it's almost true that we get a probability distribution, and that means that our probabilistic context-free grammar also defines a language model in precisely the sense of language models that we saw earlier, namely that if you take the sum of the probabilities of all the sentences generated by the grammar, giving this restriction, that what you get out is a language model, meaning the sums of the probabilities of all of the sentences that are generated in the language of the grammar sum up to 1. The almost but not quite is there's sort of one little technical gotcha, which is that if rules that are kind of if rules that can lead to sort of non-terminals that can loop back to other non-terminals have too high a probability that your generation most of the time is unlikely to stop, i.e. is unlikely to actually produce terminals, and so the probability mass ends up kind of being too much of the probability mass in infinite trees, and so the sum of the probabilities in the language actually comes to less than 1. But it turns out that if you just build a tree bank and estimate your probabilities for rules by counting how often things occur in the tree bank, and that's the basis of your PCFG, then there's actually a theorem that you can prove that necessarily your probability distribution is tight, that you really do define a language model in which you have the language of the grammar add up to probability 1. Okay. So what we're going to do then is we've got words, we've got non-terminals dominating these words, and we're going to put probabilities on them. And so I'll just show you at the end. So what we want to do is work out the probability of a string. And the probability of a string is going to be the sum of the probabilities of all trees that have that string as their terminals, which is often referred to as the yield of the tree. And so if we have this baby example here of a probabilistic context-free grammar, and the in CNF means in Chomsky normal form, and I'll come back to what that means at the start of next time. But here's a little PCFG, and so if we have a sentence like astronomers saw stars with ears, this is a possible parse that we can give to the sentence. And I've just written next to each node what the probability of the rewrite of that node was according to the grammar. Then here's the other possible parse of the sentence. I always use these little PCFG examples. And so if we want to work out the probability of this word sequence as a language model, that its probability will be just the sum of the probabilities of the two trees. And the probability of the tree is just taken by multiplying the probabilities of all the rules according to the grammar. So you get these two small numbers, and you add them together, and this is the language model probability of that sentence according to this PCFG. Okay, so I'll stop there for now, and then right at the start of next time, we'll then talk about how we can then work with a PCFG and do a dynamic program parser which isn't exponential.